Well, let's continue where we left off. So we learned about a bunch of sorting algorithms. We kind of got a feel for how fast they were. There were some beautiful visualization examples. They were wonderful. Bubble sort's the worst, but maybe the easiest to understand conceptually. Selection sort is finding the minimum value, putting it at the index it needs to go to. Insertion sort was bringing in a new guy, bringing it down to where it belongs, advancing the frontier. And then we got quicksort and merge sort. Those were the two divide and conquer algorithms that were both recursive, that had a little helper function to help them do some things, but we got there in the end. On average, quicksort is n log n. Always merge sort, in the worst case, is n log n, but it, for that guarantee, it traded some space for time. Interesting. So let me prove to you that n log n is as good as you can get. We should care about merge sort. We should care about quicksort. You also have heap sort, remember? You learned how to do it with heaps, so you put everything into a min heap, pop it one by one. That is also n log n. That is also asymptotically optimal. That's lovely. You have a third one right now, don't you? So you can't do any better than those, but the constant out in front may be different for certain algorithms. People tend to prefer quicksort over merge sort and heap sort for that reason. But you can't do better than n log n for what's called a comparison sort. And what I mean by that is you're doing a sorting based on like a comparison operation. Like you're doing a less than to see, like, did this thing come before another thing? It's hard to wrap your brain around the idea of sorting without using less than or greater than or anything like that, but there is a way, and I'll show you a way. But if you're going to use like less than, for example, you can actually get everything from less than, right? Just like if it wasn't true for less than, then it was greater than or equal to, right? And then you can just do it the other way. And you got greater than, like you can turn less than into greater than, do the negation to get the other thing and greater than or equal to, then you got them all, right? If it's true for both of the less than or equal to and the greater than or equal to, then it must be equal to. Like you can extract everything from just less than, so just pretend you only had that. But that's a comparison sort. You're sorting using these kinds of comparisons. Less than, greater than, less than or equal to, equal to. You're comparing things to each other. There's ways to sort without doing that, surprisingly. But I'm going to show you that if you are sorting with a comparison operation to figure out where things go, you cannot do better than n log n. I'm going to show you that n log n is a lower bound. It's a lower bound, so you cannot do any better than that. You cannot push your way in lower. Okay? That's what it's going to look like. And it's going to be a lower bound. I'm going to show you that n log n is a lower bound on the number of comparisons you must make, and each comparison takes constant time, and also swapping things around will also take constant time. So that will turn into n log n, just time total, as a lower bound, which is interesting. All right. So here is a hand-wavy proof that you will maybe make more precise one day in an algorithms class. But when you're sorting something, you don't know, like when you're given like a sequence, you have not actually inspected that sequence yet, right? You haven't looked at any indices. You don't know what's there. You can't just like see it all at once. You're going index by index, like, okay, look at index 0, look at index 1. How do they compare? That's what bubble sort does first, right? You have it there. It's a black box to you right now, the thing that you're trying to sort. You have to go to indices and see what's there. The goal is to turn it into an increasing sequence, right? And you can get there by eventually looking at everybody and comparing them to each other. All right. So when sorting an array, here's the secret. Here's how I want you to think about it. When you're sorting an array, you need to figure out. You know that your numbers are probably jumbled. You need to determine which permutation the numbers are in, because then you have total knowledge of what comes before what. So, for example, let's say you've got the numbers 1, 2, 3. You know that 1, 2, and 3 are in your sequence, or just like imagine that that's your sequence. Like you got those numbers in some order. Think about all the permutations of those. Permutations. Because that's what your sequence would look like, right? It's either already in order, 1, 2, 3, or it goes 1, 3, 2, right? Or it goes 2, 1, 3, or it goes 2, 3, 1. Like every sequence can be thought of like this, right? Or it's 3, 1, 2. Or it's 3, 2, 1, right? You have those options for what your sequence actually looks like. There's a formula for it. It's a factorial, right? You got 3 factorial options if there's 3 things. That's how you can permute all those values. But what you see at the beginning of time is blank, 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 or question mark, question mark, question mark, right? You haven't looked at anything yet. You know it's one of these, but you're not sure which one. The second you know, the second you narrow it down enough to know which one of these permutations your sequence is in, then you know where everything goes and you can sort it. Does that make sense? Once you have that the knowledge of which permutation it is, you can put everything in the right spot. You know which indices they need to live at, right? Because like if you had this one, it's like, all right, I need to put the 1 before the 2, and then I'm done. The 3's already in the right spot. Like once you have that knowledge, mathematically, you know exactly how to sort it. You can swap things in the most efficient way once you have that knowledge. Okay, so the idea of doing a comparison is going to get us something interesting now. So all we can do, we have black boxes here. We have question mark, question mark, question mark. We don't know what sequence we're in right now. We don't know what the numbers actually look like. All that we can do to figure out the order of things relative to each other is to do a comparison. That's why it's called a comparison sort. So for example, like bubble sort, the first thing it's going to do is look at those two guys and compare them using less than. So that's something that you can do. You can ask a question of a couple indices, and then you know their relative order. Does that make sense? Once you do that, you've gained some knowledge about which sequences you're in, right? You can ask that question about these two guys. Question mark, are they less than each other? Like this is index 0, index 1, index 2, go to them. Look at index 0 and 1. The second you've asked that question, let's say it's true. Let's say less than gives you back true. Yes, index 0 is smaller than index 1. What does that do about your knowledge of which permutation your sequence is in? Well, look at all the ones. Like, try this. Is this true for some of these? For how many of them? It's not true for that one. It's not true for that one. It's not true for that one. So do you see how once you've done a less than comparison on these two guys and you said that and you got back that it was true, you've just chopped off half of the options for which permutation you're in? See that? It's kind of nice. So that is going to lead to a proof. If you do a less than comparison on two indices, at best, that's going to cut the number of possibilities of which universe you're in for your numbers, the order of them, in half. Does that make sense? You can have two equal-sized groups, one where it was true, one where it wasn't true, and it might not be true. You might be in the other universe right now with your numbers. Who knows? So that means that if you make, like you know that you're in one of these now, if you make another comparison, you can chop that in half again. You do the right one, maybe, at best, right? So does that make sense then that if you make X comparisons total, you can chop off 2 to the X. Wait, let's see. I don't want to say that. If you make one comparison, you've separated the numbers into two groups, yes? You make one comparison, you've separated the numbers into the true groups and the false groups. If you make two comparisons, now you can separate between 4 different groups, right? Either it was like, it was true the first time, then maybe it was true the second time, then it was false the next time, or it was, I don't know. It was false the first time, then it was true the second time, false the third time. You have 4, like it's cutting it into 4 groups essentially at that point. If you make 2 comparisons, like was it true, was it false? So therefore, in total, if you make X comparisons total, you make one comparison, you can distinguish between 2 to the 1 groups, 2 groups. It's always going to do powers of 2 now. So X comparisons total, you can distinguish between 2 to the X different groups of numbers. You can see, you can cut off and separate it in that many different ways, all right? Your goal for figuring out which permutation you're in is like, you want to split off the numbers into n factorial different groups, don't you? Because that will cut them off perfectly, and then you'll have them all separated, and that will be how many comparisons it took to separate it in a way that you know exactly which permutation you're in, okay? If you did that, you would have used a certain number of comparisons to make it happen. And we know that a good bound would be 2 to the X comparisons will give you that many groups. It'll separate by that many groups. We want to solve the equation 2 to the X equals n factorial. I hope that makes a little bit of sense. This is very hand-wavy. Like that's what I'd like to have right now. All right. That would tell us how many comparisons at a minimum, because sometimes it doesn't perfectly cut it in half. That would tell you at a minimum how many comparisons you needed to sort the array to figure out which permutation you're in, assuming that that's what's going to give you sortedness. So you'll know what the right order is at that point. Okay, you need that. You need that total knowledge of who comes before what. So we want to solve this equation, 2 to the X equals n factorial, where X is the number of comparisons we need to make. Because we'll be able to distinguish between 2 to the X different groups every time we make we make X comparisons. And so to solve this, we can take logs, right? Logarithms of each side. So take the log base 2 of each side. We get x on the left is equal to log base 2 of n factorial on the, n factorial on the right. This is disgusting. I don't know how to simplify log base 2 of n factorial, but that I know is going to be greater than log base 2 of, how about this, n over 2 to the n over 2. Let me prove to you that that's bigger, or that this one is smaller. Watch. If you think about it, n over 2 to the n over 2 power, I'm just trying to get the proof to go through right now, I'm picking a good number. That's going to be less than the following, right? We're trying to say that it's less than the factorial of n times n minus 1 times n minus 2 all the way to 1. And the reason that's true is because think of all the numbers, there's half of the numbers that are bigger than n over 2, right? And you've got n over 2 of those. Cut these numbers in half. Boop. You got a bunch of numbers that are bigger than n over 2. Just replace them with n over 2. That's for sure going to be smaller. Does that make sense? For sure going to be smaller. It's like you've taken these big numbers and you've replaced them all with n over 2, n over 2, n over 2, n over 2. Replace half of them. The factorial is way still bigger than all that. Yeah? It's even got more things on the right. It's like that inequality holds. And I can find, because I'm looking for a lower bound anyway, it's fine. I can find the log base 2 of that quite easily. That's equal to n over 2 times log base 2 of n over 2. And constants don't really matter. That's about n log n. So that's a very hand-wavy proof. But I hope it made a little bit of sense. Every time you make a comparison, you've cut off half your options. And so you're able to distinguish between like the true groups and the false groups. It's always like you make another group out of the deal. All right, so you can distinguish between 2 to the x different groups after x comparisons, because it's always doubling the numbers of things that you can distinguish based on was it true, was it false. And we want to distinguish between n factorial groups, because that would tell us exactly which permutation we're in. So we solved for this, and it looks like x, the number of comparisons we need, is on the order of n log n. N log n comparisons where it's constant time to do a comparison and also to swap once we know which order is right. That means that n log n is a lower bound for the number of comparisons we need to make here. Does it make at least a little bit of sense? Then we know what permutation we're in, then we can sort based on that. We have total knowledge, we know who comes before what. We need that. Otherwise, if there's always a question mark, like if we didn't make enough comparisons, we're not sure who's over here, where it belongs. Like it could go at the end, it could go at the middle, it could go at the start. You need to know the final permutation. Otherwise, you're not sure where everything goes. So you need that total knowledge. Yeah, that's why n log n is the best you can do for a comparison sort, but it's not the best you can do for every type of thing. There are some sorting algorithms that work without comparisons. Would you like to see one? Are you ready for that? Yeah. I will not test you on this one, but it's a weird one. All right, it's called radix sort. Feel free to look that up and try to find it in, I don't even know if it's in your book or not. I can't remember. Maybe. Go look it up on the internet, worst case scenario. What radix sort does is it gets it down to linear time for integers. If you want to sort integers, there's a trick. All right. So the secret is that, I mean, it's making the case that you could only have that there's a limit. It knows that there's a limit and it takes advantage of that limit. You don't have an infinite number of values that you could possibly have as integers. Say that you were sorting unsigned integers or something. Just imagine that an int as well, it doesn't matter. The biggest unsigned int is a little over 4 billion, or a bit over 4 billion, however you want to think about it. That is a 10-digit number. And the number of digits in any int, therefore, is a constant. I have 10 digits max per integer that I want to sort, if it's integers. Okay? So what radix sort does is it loops through each of the digits from least significant to most significant, and it's going to put them into buckets based on what digit it sees. So here's how I want you to think about that. Gosh. Yeah, I'm going to show you what that means. So there's going to be 10 buckets total, because you'd have 10 different digits that you're looking at. So I was going to look at a certain place of the numbers, and it's going to loop through how many maximum digits there are, And it's going to go through the array that many times. So if there's 10 digits max, it's going to go through the array 10 times n times. And I'll show you that. So let's say that our numbers that we would like to sort look like this. They're 3-digit numbers max. Then we'll have to loop 3 times through all the numbers. So 489 and 713 and 147. Let's say that those are our numbers. If there are any smaller numbers, like 27, you just put a 0 right there. Still pretend that there was a digit there, and you really do that in math, right? And so what it does, what this loop is going to do, if you look into it, it's going to start with the least significant digits, so the ones placed first, and it's going to put them into buckets based on what digit is there, and it's going to put them in that new order based on the order of those digits you're looking at. So there's going to be, I don't know, there's going to be a 3 bucket, like the last digit of the 713 is 3. There's also, it's going to go in order. Like there's a 0 bucket, a 1 bucket, a 2 bucket, a 3 bucket, all the way to a 7 bucket, all the way an 8 bucket and a 9 bucket. All the numbers that end in those, that have a digit that we're looking at that has that one, go in that bucket. That's the technical term. So for example, we're going to loop through all these numbers. We see that 9 is in the place we're looking at right now. So 489 is then going to go in the 9 bucket. You'll place it there. And then 713 ends in a 3. We're looking at the ones place right now, so it's going to go in the 3 bucket, 713. And then the 7 bucket is the one that 147 is going to go in. All right? And so if you take these numbers back out and put them back into the array in that order, in bucket order now, you're going to turn this into 713, 147, and 489. So now they're sorted on that digit. Does that make sense? Because the buckets, of course, have an order. Just keep that in mind. And then what the algorithm does is it's going to go through the numbers again, but on the next digit. It's going to put them into the right buckets and read them out. So this one's going to go into the 1 bucket. Does that make sense? This one's going to go into the 4 bucket. This one's going to go into the 8 bucket. And they're going to be read back out in order of the buckets that they were placed in. And we just got lucky and they're in the same order. We'll just read them right back out. So 713 is still there, still first. 147 is still next. 489 is still last. And now we consider the last digit, the most significant digit. 7, 1, and 4. So this one's going in the 7 bucket. This one's going in the 1 bucket. This one's going in the 4 bucket. And then you read them out in that order. So that turns into 147, 489, and 713. Ta-da, they're sorted. So you went through all n numbers, n, as many digits as there were maximum times. So this was 3 times n, which was a linear algorithm. Does that make sense? So for n's maximum 10 digits, you're just going to do that up to the 10th digit place. That's kind of cool. And what you were doing with these other ones, with these other digits, was making sure that if they ever agreed on something, if it was if this was 143 and 147, the previous buckets would have made sure that the 43 came before the 47, even though, just due to the way that you're going to add them to the buckets. That's what the previous digits were doing, even though you really only needed the first digit for these numbers. If there were any commonalities, that's what the other things were handling. But yeah, that's kind of the algorithm, and I hope you see that it's a linear time algorithm. We're taking advantage of the fact that there's a maximum number of digits per this per number we would like to sort. And so that turns into a linear time algorithm, which has been sorted without ever doing less than. It's a non-comparison sorting algorithm. And I think you can imagine you cannot do better than linear. You got to go through all the numbers at least. So that's for sure a lower bound. So yeah. Any questions about radix sort? Cool to think about. Doesn't have to be decimal also. Remember that numbers are stored in binary. So there's a binary radix sort. So there's a 0 bucket and a 1 bucket. And integers are 32 bits long. So you'd have 32 rounds of playing that game. That would also work. So yeah, that's all that. Are we ready to just talk about algorithms in general? So I'd like to zoom out a little bit. That's where we're going today, not the world's most... just a bunch of weird topics. I like it. So you'll get well acquainted with all this in a future class, I know. But let's talk about it for now. So here is what algorithms are all about. Just remember, algorithm, all that word means is it's just like it's like a recipe. It's a sequence of instructions to solve a problem. For us in this class, it's perform computation that gets us some answer we want. That's all an algorithm is. And we know now the whole point of CSCI 41 on top of 40 is that we can analyze algorithms. So we know that there's a million ways to do the same thing, but some ways are better than others. Yeah. So some algorithms are very slow, some go fast, some use a ton of space to do their job. Some of them don't use as much space. And there's always usually a trade-off involved. We know that now. Some problems we can prove that, yes, for sure, this is an n-squared algorithm. This for sure, there's nothing better than n-squared. Yes, this for sorting, comparison sort cannot be done any better than n log n time. We can prove that. Some of them, like we can tell, we know that there's sometimes there's a trick for certain classes of problems to make them extra fast. Like we can turn sorting into linear time if we take advantage of something else that exists in the problem. And a fun fact that maybe you haven't really thought about yet is that there are some problems that we have algorithms for, but we're not sure if those are the best algorithms still. We're not actually sure. If you've heard P equals NP mentioned on the internet, or in a TikTok, this is that idea. All right. So there's a whole class of problems where our best solutions are like exponential time. We're not actually sure if that's good. Maybe there's a polynomial time one, if only. But we have no clue yet. Most people are most computer scientists at this point. They are pretty confident that P is not equal to NP, because otherwise surely we would have found one good algorithm by now. But you never know. You never know. So all right, let's talk about some kinds of algorithms that make things cool and fast. This is a fun adjective. There's a class of algorithms that are called greedy algorithms that kind of zoom in and try to solve a problem in a very in a myopic way. I think that's the word, right? Let me use my dictionary. Yeah, that means short-sighted. So zoom in. You can't see much, but you can try to come up with an algorithm that just looks at a small amount of information and ends up solving it in the most optimal way anyway. That's called a greedy algorithm. Like you just got lucky. It's really cool. A greedy algorithm is one that makes a locally optimal choice, one that looks good for me right now. Like I'm going to eat ice cream right now. I'm going to do it. And it ends up leading to the optimal outcome of the final solution, surprisingly. That's called a greedy algorithm. You don't have to think much, but you get the answer for free and fast. All right. So a good example of a greedy algorithm is for at least for American coins. If you want to make change in the fewest number of coins, the greedy algorithm is just like start with the largest number you have of coinage, like a quarter, or I guess maybe if you have a 50-cent piece, go for that, and just keep on using the largest coin until you can't anymore, then use the next largest as you need it. That will always end up giving change in the fewest number of coins, or at least for American coins. And we can pretend we live in a place where that we don't have 25-cent pieces, but let's pretend we have 20-cent pieces. I forget which countries have that. Is that the UK or the Eurozone? I cannot remember. But this is an algorithm. It's like, all right, I want to give change for 36 cents. You can never do better than just keep taking the 20 if that's the biggest one you got. All right, take the 20. Now I got 16 cents left to give. Then give them a dime. Now I got 6 cents left to give. Give them a 5. Give them a nickel. And then I got 1 cent left to give them a penny. You can never do better than that. That's always going to be optimal for certain kinds of coins. So like for 56 cents, for example, that's just another 20. That's not a percent. That's a cent, isn't it? 56 cents. That would end up like, all right, give them 20, 20. I can't give them another 20, then start with tens. All right. And then can't give them another 10. Let's give them a 5, then a 1. Something like that. And the proof is involving the idea, like the fact that, okay, there's no other good way to do this. Like think of all the other options. what would have happened if you had some other option for these would have been something like this. Like you gave them, like you can't just like turn this 20 into something else that's better overall. Your locally optimal decision led to the globally optimal outcome. You can't like turn this 20 into like 2 10s. Like that's as good as you can do that. Now you've used more coins. Something like that is the proof that it works. But there are certain coin denominations that this algorithm doesn't work for. It does not always give you back the least amount of coins for a certain amount that you need to give back. So it doesn't always work. You have to prove that it works. But it's quite nice. It's a very simple algorithm, isn't it? Like if you're a cashier in America, at least. Say you had disgusting coins that look like this. You had a 4 cent coin, a 3 cent coin, and a 1 cent coin. If you use the greedy algorithm to make change for 6 cents, you'd give them a 4 coin and then 2 1 coins, wouldn't you? But you know that there's a better option. You could have given them 2 3s. So that's not always going to work. But if you can prove that it does, you're in good shape. And it's a very simple algorithm. That's called a greedy algorithm. You're making a locally optimal choice. Like, all right, how much do I have to give left or right? Give and change remaining right now. Okay, I'll choose the biggest denomination I can find. And I'll keep doing that. I'm just gonna I'm not gonna think ahead. I'm not gonna think about the big picture. I'm gonna look at the small picture, and it ends up working out for certain kinds of problems. It also ends up not working out for other kinds of problems. You have to prove that it works for the one you want to solve. All right? Does that make any sense? That's a greedy algorithm. It's just a word that describes certain kinds of problems where you don't have to look too far ahead. I'm sure some examples of problems that you've done already that don't come to my head immediately are greedy algorithms. Let's see here. To contrast greedy, sometimes you have to do it the full way. There's a way to get there's a way to come up with 3 and 3 here, and the answer involves what's called dynamic programming. It's a disgusting little buzzword that somebody came up with one day just to make their boss think that they were doing something important. That's legitimately the story. So look it up if you would like. Dynamic programming is wonderful. It's a rainbow. It solves a lot of problems, but it's a little weird to talk about. So dynamic programming has nothing to do, the word dynamic means nothing. It's meaningless. All of our programs are moving around and doing things, right? So dynamic is a useless term here, but it's turned into a description of a certain kind of algorithm, right? Dynamic programming problems are when you're solving them using smaller versions of themselves, so that usually they're going to end up recursive, but there's a way to turn it around on its side and not make it recursive, but still you think of it that way when you're defining it. And here's what it means to be a dynamic programming problem. In addition to using smaller versions, you find the problem within itself, and then also the problem exhibits optimal substructure and overlapping subproblems. The best example of this is going to involve you trying it. So let me at least say some words and then we'll give this a try. So the solution is built up using the solutions to smaller subproblems. So that's what's called optimal substructure. We can use smaller answers to build up our bigger answers. So technically, recursive algorithms that we've done exhibit optimal substructure, but the overlap is the new thing for dynamic programming. So overlapping subproblems means that when you have a recursive algorithm, you're going to implement this recursively because it overlaps. The naive version of that would just keep getting called on the same input. You'd keep getting down to the same things a lot of the time because they would end up overlapping a lot. So if they didn't overlap, you would just use divide and conquer and call it a day. But dynamic programming is when they do overlap. So this is this is divide and conquer, you merge sort, chop it in half, solve that half, and bring it back together. That is when it's non-overlapping. When it is overlapping, that's when you reach for dynamic programming. So that's when you've got, you can split it up into not quite half, but a little bit more than half on that side. That's your green half. And then, another color, red. Then a little bit over here, that's your red half, but it's more than half. And what you do when you notice that is you see that there's some overlap. The problems overlap. You can break them down to be smaller still, but they overlap on this bit. That was at the end of this one and at the start of this one. And so as you're solving these problems recursively, you're going to break it down. You're going to get to that little blue squiggle section a bunch of times in a bunch of different places. Does that kind of make sense because of that overlap? That wasn't true for most of the algorithms that we talked about so far. These are new kinds. All right. So yeah, the way that you can still make this nice and efficient, the solution that dynamic programming gives us, the reason that this got a name, is that what we want to do is remember. We want to save the results of our smaller recursive calls answers because we might see that input again given to us. Like on this side, it might call the recursive function on the blue part, and on this side it might do it again. You might see that same input again. Save the output you got over here so that you don't have to recompute it. That's what dynamic programming is all about. Save it in a hash table. There we go. So yeah, that's the secret. That's what you do. It's like you make a table. That's really honestly the answer. If you see the blue problem, here's the blue problem's answer. If you ever see it again. If you see the green problem, I'll save away. Like if it's not there yet, go and compute it. But once it's computed once and for all, it's like put it in the table. Put it in the table. It's got an answer now. If you ever see it again, go consult the table first. You got an input. It was the red input. Oh no, there's nothing there yet. Let's go compute the red answer. Once I get it back, I'll put it in the table so that next time I see the red input, I will have an answer to immediately give back, constant time. I never have to recompute it. That's the goal of dynamic programming. And we can actually do that for Fibonacci. That's the one example that I showed you once. Remember that recursive Fibonacci code? Yeah. That would take longer than the universe has existed to complete. Dynamic programming is the answer. Because you got down to that base case a million different times. You got down to the smaller calls a million different times. You saved the answers, checked if they were already computed, gave that answer back, that saved answer back, then you're good to go. All right? So let me force you to think about these problems. Here is an example of a greedy problem. So there's a website called leetcode.com. Have any of us heard of that? It's like a place to practice your data structures and algorithms because that's what people like to give you in software engineering interviews, these kinds of questions. So I'm going to give you these links. There's a few of them. I think you can at least look at the problem yourself, but I'll give you these links. Maybe I think we're already on the attendance, so let's go to the written nice page. I'll just put it on the written nice page for us. Boop. Here's the first one that I want you to think about. It's called is subsequence, and then this one is a climbing stairs. So let's look at the first one now. Boop. So there it is. So is subsequence. Go to the written nice page to get that. Here it is. Of course, it's in dark mode. It's probably not easy for you to see it. I like dark mode, but why don't we have an option? I guess all we get is dark mode, as far as I can tell. Sorry about that. If you find it, show me. But here's the question, all right? I want you to think about this for a bit. You don't have to solve it. We're on the first one. This is a greedy problem example, all right? I claim that it's a greedy answer called is subsequence. It's and then here's the description of it, all right? So you're given two strings. Here's the function you're trying to write right now. It's a greedy problem. So you've got two strings, s and t, and you're supposed to give back a bool, true or false. And you want to return true if s is a subsequence of t. So s is like the smaller string in theory, and t is like the bigger one. You're looking and seeing that if s is a subsequence of t, and what subsequence means is that it's a piece where you've chopped off some characters in order of the original string. All right. So for example, ace is a subsequence of a, b, c, d, e because you can take the a and then the c and then the e out. It was in order. You've like chopped off some characters. This is a subsequence of that one. Does that make sense? But AEC, even though it has similar characters, it didn't go in the right order. So that's not a subsequence. So here's some example inputs. ABC is a subsequence because there's the A, there's the B, there's the C of the bigger string. For this one, AXC does not work because there's an A and there's a C, but there's no X in the middle between them. Does that make sense? And it's also telling you some constraints about the sizes of these strings if that helps you come up with an answer. Like, oh, this is not too big. I can make I can make an array or something. This one is kind of huge. Maybe I shouldn't like try to save all the answers somewhere. But yeah, that's the question. That's the problem. Go to that page and think about how you would solve it. The answer is you can just you can forget about the rest. There's a way to zoom in and think about the problem at hand right now, and that will lead you to the optimal answer. It's a greedy solution. All right, so give that a try. Think about it. Discuss with your neighbors how you might go about solving it just in English. Like try some examples. Do this one and try to walk through how code might work to discover that ACE is a subsequence of ABCD. That would be a good example. And then I'll show you my answer in code. This may be your life one day if you want to be a software engineer. You're going to go to an interview, you're going to get a problem like this, you're going to solve it, and then you're going to analyze it. You're asked to analyze the running time, and space complexity. Good practice. This one you can be greedy, but don't you think too hard. At least you're broken. You don't have to code it, but just think about in English. All right, our voices seem to all die down at the same time. Let's look at this. So, can anybody, any brave soul, describe to me, like, all right, I got this one. How do I go and I notice that it's like A, H, B, G, D, C? I don't know. How do I find this in that? Any thoughts? Yeah, you want to go through, you definitely want to go through all these characters, right? Because you're looking for them all in this, yes? Can you focus on one at the beginning? Yeah. That will lead.
It works like we just move on to the second.
Yeah. Let me try to say that louder for the people in the back. So here, what we got is, here's our greedy solution. Just like, all right, we are doomed if we don't find the A, right? Go find the A. Cool. There it is. All right, now it's time. If it's a subsequence, then I should see a B next, right? Now go looking for the B after that. All right. By hello, I found the B, right? Now it's C's turn. You see how you can zoom in and look at just the next character you need to find? Go looking for that now. Like, all right, no. Oh, there it is. And then once you've exhausted the string, you're good. You found every character in that right order. Yeah. So that's your greedy solution. Only try to find the next character you haven't found yet. And I don't. Let's see. Submissions. Here. Here's my solution. Dun, dun, dun. Can I see that in a bigger way? There we go. I was like, all right. Empty string. Special cases, of course. The empty string is in everything. Nothing else is in the empty string. True, false. And that's always like, all right, what's the index of the character I'm looking for? What's the current index of the string T that I'm trying to go through? It's like, all right, as long as I can go through and like I got an index I'm looking at. All right, here's the character I'm looking at. That could have, I guess, been taken out of the loop. That's a little inefficient. And it's like, all right, if I find it at this index of T, the bigger string, if that's equal, then go looking for the next one. Go advance the index of the character I want to look for. And then also advance the index that I'm looking at in T, because I've used that character up. Either I matched it against something or I didn't. I chopped it off. One way or another, I'm done with that character now. So I'm like advancing through both strings at once, in a sense. It's possible that we just ran out of, like if we advanced index of character I'm searching for, if we just ran out of index of characters to search for, then it was a subsequence. But if we ever get out of this loop, that means that we didn't return true and pass all the characters of S. That means we just exhausted T without getting past all the characters of S. That means we're done. False. Something like that. So that would be a solution, and that would be a linear time solution, wouldn't it? Linear in the number of, like, the bigger of the number of characters of S and T. So you're going through both of them. Something like that. Does that make sense? So that would be an answer. Here is the small version of that if you want it yourself later. But that's the idea. All right. So do you see why it's greedy? It's like you can just zoom in, look at the next character only. And you kind of see how we can analyze that. So you're looking at indices as well. So it's constant time, constant space, linear time, and the number of, like the maximum number of characters in these strings. Something like that. Something like that. Any questions about this example? So yeah, try it. There's like a top 100 problems list on LeetCode. You guys can solve most of them by now. You know about hash table. You can use the C++ standard library. You know about a lot of things, a lot of different data structures that give you some good speeds on things. I think that would really help you practice. All right, here's the next one. It's called climbing stairs. This one is secretly one that you already know, but here it is. Oh, nice. Somebody was inserting their answer. I like it. Here's the climbing stairs problem. It takes an int, gives you back an int. You're counting all the ways to do something here. So it's like you're climbing a staircase. It takes n steps to reach the top. And every time, like if you're in a hurry, you can go up 2 steps at once or something. But every time you can make a choice, every time you got a new step to go up, you can either climb up 1 or 2 steps total. Right? You can either like go up 2 steps or just go up 1 step. And then you always have that option no matter what step you're at, unless it's like the last one, then you can only go up 1 more, right? The question is, how many distinct ways can you climb to the top? So let me try and help you understand. Like here's a staircase. But I want you to discuss this next once I explain it. Like here's a little staircase. Let's say there are 3 steps, and here you are at the bottom. you can either go up 1 or 2 at a time, right? So you're always starting here. On your very first step, you can go to here, right? Or you could have jumped, gone by 2 and gone straight to there, yes? Those are your two options. And then once you're here, you can go up 1 to get to here, right? Or you can go up by 2s to get to the very top from that step, right? Those are more options. And then from this last step, you can only go up 1 more. Do you see that? And so it looked like you're just counting all the different ways you could have done this. I think it's 5. Because it was either 1, 2, that's one way, or it was 2, 1, or it was 1, 1. Oh, sorry, I think it's just 3. Yeah, it's just 3 ways. Or it was 1, 1, 1. Does that make sense? 1, 2, yeah, 2, 1, or 1, 1, 1. 3 ways total, and that's something you get back. So there, the input would have been 3 steps, and your output also would have been 3. There are 3 ways to do it. Does that make sense? So that is the idea. So if n was 2, there's 2 ways to do it. You could do 2 1-steps or 1 2-step. N is 2, you give back 2. If n is 3, you give back 3 for this exact reason. Yeah, you can go 3 1-steps, 1 step and then a 2-step, or 2 steps and then a 1-step. See how those are all distinct ways of getting to the top? Different ways of doing it. So there might be some overlap. So maybe it's a dynamic programming problem. So, because the second you've gone up 1 step, now you have these options, right? It's the same as after going up 1 step and seeing these. It's like after 1 step, you still have the same universe. You can get there in 2 different ways, kind of. Yeah. So it looks like the n values are going to be quite small. So I guess you can do it by hand. That would be the actual solution. If you're guaranteed to have n values that are this small, it's like solve the problem manually for each of them and make a hash table or something. Just read it off. But I think it would be fun to think about how to do this. All right. So stare at this problem for a few minutes. Think about your answers. The hint is that it's going to be dynamic programming, which means it's recursive. So I think what you should focus on is figure out the recursive solution first. You don't have to worry about like dealing with the overlap, because there will be overlap, but try to find the recursive solution, because that's what's going to lead us to an answer. All right. So figure out the base case, multiple base cases potentially, and then the recursive case. So your goal is to give back for a certain number of stairs. How many need to go down? Or how many different ways to get you up those many stairs? Or you can go by 1s or by 2s. Discuss base cases and recursive cases.
Let's see the picture in your head.
Pictures might help here. All right, let's think about this. It looks like we're always going to have at least one stair to climb as our input. Always at least one stair. So I think that's probably a good base case for sure, right? How many ways are there to climb one stair? One way. Nice. And then let's assume that that might be all we need, and let's deal with the recursive case. All right, we have n stairs to climb. What are our thoughts? Did we figure it out? Do we have any ideas? Okay, n stairs to climb. And we need to turn this into like a recursive call on a smaller number of stairs, right? Something like that. Because that we could assume we got the right answer back and build it up bigger that way. Something like that. So let's see. Here's the intuition. This is hard, I know. Here's the intuition. Say, all right, you've got n stairs to climb. How many ways are there to do it? Well, if you think about climbing all the stairs, and then you're on the last one. It's like figure out all the ways to climb all the stairs up to the n-1th one, because then take all those ways, you just like add another step. Does that make sense? So that's all the ways to get up to the very top where you came from the n-1th stair. It's just the same number, right? Because then you just like, you're always forced to go one more. And there's only one way to do that. So all the ways to get up by n, if the last step is a single step, it's just like, you came from the n-1th step. Does that make sense? You came from the n-1 step. What are all the ways to do that? And then like you're always forced to add one more step, so that doesn't add to the number. Alternatively, you could have come up, you could have come to the n-2 stair, right? Something like that. Because you could have come and you could have gotten to the last one with a 2 steps, right? So that means that you came from the n-2 step, right? Something like that. So you solve this problem, n-2. You came from 2 steps ago, and how many ways were there to do that? You're tacking on always 2 steps from there to get to level n from n-2. So it's just as many ways as there were to get from there, because you're just forcing that last bit on top of all the other ways. Like whatever ways there were before, like count them all. It's like you're always adding one more 2-step on top of that. So it doesn't change the number of ways to get to that step coming from 2 steps ago. I know is a little hand wavy, but that's kind of the idea. It's just like, all right, you could have come from 2 steps ago or from 1 step ago, and it's just however many ways there were to get to 1 step ago, plus all the ways that there were to get from 2 steps ago. Because say you had all those ways, you had the count for 1 step ago, all those ones. The way to get from n-1 to n is like you're forced to add one more. It's just like take all those other ways and always add one more on top of it. It's like you have the same number of ways that you had back then, if that makes sense. You're not changing it. It's just you're adding that to 2 steps ago as well. Something like that. So that's that one. And if you're going to do n-2, that implies that we need another base case, like p of 2. Because like if we were asking for p of 2, we would have needed p of p of 1 and p of 0. I guess you can have p of 0 be a base case, but you need at least another one. And so if it's going to start at 1, you're going to need, I think 2 would be a good one. Let's see. Does that make sense? At least a little bit. Oops. How many ways are there to get up 2 steps? You can go 1, 1, or you can go 2, right? There's 2 ways to do it. And then number of ways to get up n steps total is, I guess you kind of think about it backwards. Like you could have, that's probably the easiest way. It's like either, here we are on the nth step, either I came from this step or I came from this step. N minus 1 ago or n minus 2 ago. And just like count all the ways to get to here. I add 1 more step and I'm there. Or count all the ways to get to here. I add 2 steps. I take a double step and now I'm where I need to be. So it's just those ways added together, if that makes enough sense. That's going to be the secret. And so that turns into this problem, which should look familiar. Have we seen this problem before, this recursive problem? If we look on the next slide. It's actually just calculating the Fibonacci number secretly, which is fun to think about. Dun, dun, dun. We can do this a bunch of different ways. We can do it the slow way or the fast way. Do I want to do any of that with you right now? Not really. I guess we could code it up and do it wrong, but yeah, if you do it the naive way, then you're going to get disgustingly exponential time, because like here would be your answer. All right, the ways of 1 is 1, the ways of 2 is 2. Those are your base cases. And then in the recursive case, it's like ways of n is equal to call ways of n minus 1. Oops. How did that even happen? Ways of n minus 1 plus the ways of n minus 2. Like that's the answer. That's the recursive case. And that would overlap really badly. So for example, say we're asking for the ways of 5, where P is our problem's name. That would go off and it would call P of 4, and it would add the answer to P of 3 to that. And then each of these would have to complete themselves, wouldn't they? We've been here before. P of 4 would call P of 3 and P of 2. And P of 3 would call P of 2 and P of 1. Now it's 1 and 2 are the base cases, so I can stop there. P of 3 would also call P of 2 and P of 1. And those are your base cases. So notice that you got a bunch of duplication of these calls to the base cases, right? You have all of P of 3 over here and duplicated. That's disgusting. And it gets even worse the more you call, right? If this was P of 6, you'd have P of 4 over here. You see that? That's wrong. That's not good. You'd be duplicating all this work. Like you went and you found the answer to P of 3 on this side. Just like remember the answer so you can cut this all off. Does that make sense? That's what you want. You want to cut off things that you've seen before. And that leads to an answer. So yeah, if you save the intermediate results, then you're good to go. Where can I find my submissions? So here's like the bad way. That's this one. And it's like time limit exceeded. It went too slow because we know that it gets to be exponential time. Like this is the naive solution. It works. It will give you back the right answer if you wait long enough. We don't have that time though. But this is the right answer. And then if we, instead of that, oh gosh, how do I get back to my submissions? Exit? Yeah, there we go. If we get to this one now, dun, 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 or even this one, are there any other ways I can do? What's the best way to say this? Unordered map. Normal map. Yeah, let's do this one. That's probably the best answer. So here's the secret now. Just as like a global variable, the answer is just like save your intermediate result. So like if you ever ask for P of 3 again, like you solved it here, when you ask for it, like don't go down this chain anymore. Just like remember the answer, read it off a table. That's the solution. That's what you want to do. So look at this. So you have like an unordered map that holds your answer. So inputs to outputs, key value pairs, call it M. We're remembering things. This is our memory. And yeah, it's just like if the value is like 2 or smaller, I guess, return 1. So I did a weird base case. I did 0 and 1 as a base case. So that's just the Fibonacci number. So that will work still. That's fine. And then for anybody else who's not a base case, before we ever try to do the hard part, the hard recursion, go and look in our lookup table and see if this input is there. see if it's there or not, because that's where I put the answer if I made one already, if I got the answer already. If it's there, return it back. This should be m.at_n, but I was trying to be fancy. m.at_n, go there, go to that place of the hash table, find it, and yeah, otherwise you have to do it the hard way. But once you've done it the hard way, get that answer and save it away so that anybody who ever comes back again can remember that this input here was their proper output for it, and then you can return it as you needed to this first time. But that helps you cut off the problem, and then it turns it into a linear time solution because it'll look like this, like P of 5 will then call P of 4, which will do the hard work, which will call P of 3, which will call P of 2, that's a base case, kind of. P of 3 will call P of 2, P of 1. So that's all the work that will ever be done because P of 2, P of 1, those are base cases. That's fine. P of 5 will call P of 3 here, and it will just be done. Like, it has the answer saved away already right there. And so it's like 2 times n calls or something like that, which is not bad. That's a linear number. So it's much better. You don't go too deep. That's wonderful. So yeah, that turns into linear time, more or less. Okay? Any questions about that? If you save the results, because you knew that there were some overlapping subproblems, that's the secret. Save those results, you will remember. All right. I think that's what I want to say. Questions about this example? It is kind of hard to explain why it's just like n-1 plus n-2 without any extra like plus ones or anything. But this was, hopefully this drawing kind of helped. Either you came from here or you came from here. And all right, give me all the ways to come from here. There's the same number of ways to get to the top from there. So just one extra step. Same number, you're not adding anything. Just the other option. So yeah, the last thing that I want to talk about today is I want to teach you how to use the terminal better, because that's part of the requirements for this class. You've trudged along so far, you've made it all work for yourself, but there's some cool things that you can maybe do that you haven't been doing. So let me show that to you, though. This will take up this time and a little bit of next time. So let me show you some cool commands that maybe you haven't seen before. You can read more about them. Look at their manual pages, of course. These are all options. But let me show this to you. Let's see, what's the best thing to do here? Yeah, I think that'll work. So sure. The first one, the simplest one, it's called echo. What it does is just, you give it some command line arguments and it prints those back. So you can say echo hi, and it prints hi. Hi mom, it prints hi mom. Just like it prints whatever you give it after the name echo. That's kind of cute. I'll use that later. Cat is short for concatenate. It outputs the contents of a file to the terminal. So let's get a sample file. Dun, dun, dun. I'll call it file1.txt. With a few lines. This is a file. Dun, dun, dun. So there it is. If I see it there, I can cat it. I don't have to go into Vim if I don't want to. It just like prints the entire file to the screen. I may have shown you that before. There's that one. There is always a manual page for all of these commands. You say man space, the name of the command you want to look at, man space cat. Like look up in the manual the cat command, and it looks like you can give it some options, and then you can give it multiple files, and it'll output all of those files at once to you. That's kind of nice. Here are some things that you can do to cat, like dash stuff. You can ask it to number the lines for you. That's cool. I didn't actually know that. Cat dash n on file 1. Whoa, I like that. It's kind of what Vim's doing for you. That's neat. Yeah, so that's manual page. You can do that for anything like man ls. What can we do there? Man g++ is disgustingly long. These are all the options you could give to g++. Wow. Different options, different things it can do. And then time. Time is a cute one. It lets you just like time how long something took to run. So what's a good example? Let's make a C++ program really quick and we'll time it, how long it took. Example.cpp. Like let's ask it for two. Let's have it let us enter two things, and it will output their sum or something simple like that. There's my example.cpp. And so instead of just running it by itself, 2, 3, we could have it run. We can give it to time. Say time and then give the same command, and we'll time how long it took to run. Yay. So here it is on the top now. You can say time that thing. All right, and if I hit enter, now it's running. I can say 42, 43, 85. And it's like, it's keeping track of, well, it took about 3 seconds total for it to run, but it's also keeping track of how long the program itself was executing, because it was waiting for my input for a little bit, and it doesn't really it doesn't count that. It counts that separately. It counts that to total time, but not actual like system time, if that makes sense. So that's why it was quite quick. Time ls. Oops, time ls. Very fast, but it looks like it took that long to do its output. That's cute. So yeah, you can time things pretty quickly with that command. That's nice. I think that's most of what I wanted to say. What else? See any questions about those? Just some commands that do things. You can look them up in the manual pages. It's quite nice. Here's where things get fun. We can do less than and greater than, and also a thing called piping. So here, let's talk about that. So in Linux, so first of all, on our server, we are running an operating system called Linux, just to make sure we're all on the same page. It's a nice free operating system that drives pretty much every server on the internet, because you don't have to pay anybody for license fees. And it came from an earlier operating system called Unix. There are still a bunch of operating systems that are Unix-like in that regard, but Unix used to be like made by AT&T. It was copyrighted, and just Linux stole a lot from that. And in Unix and Linux, everything is a file. So you can basically get away with pretending most things inside of your operating system, if it's Linux at least, is a file, and you can like read to it. You can write to it, read from it, write to it. And it's really cool. You can pretend that like the output of a program or the input to a program is a file, and you can do that. You can give it to that program in that way. So for example, you can run a command. You can say less than, which is like an arrow. Read it like an arrow. It gives the contents of a file to that command as input. It's like it typed it for you. That'll work like that. So give the file to the command as it runs. That's kind of neat. So, I don't know. I just ran example with 42 and 43 to produce 85. Let's make a file, file2.txt, with 42 and 43 in it, with a bunch of weird white space, space, tab, 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 new line, space, tab, 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 42, 43. There they are. It just needs them eventually. That's file 2. I can cat it up so you can see it, right? I can say, run the program with file 2 as input, instead of me typing things. And it makes the 85. It finds the two things. Isn't that cool? That's, you can give a file as input. You can also do the opposite. You can take a program, you can run it, and have the right arrow, right? That is going to output to a file, all right? I'll run it, it will output to a file, okay? So like /example and outputs to, I don't know, something. Example output.txt, something like that, 42, 43. And so we don't see the output when we run it because it got redirected to there. They have a new file now, example output. There it is, got the 85. You can say ls. Hey, ls, output your file to ls output.txt. And it runs and it doesn't produce anything, but it made a file, and we can look at that file, ls output. There it is. Cool. So that's useful. Questions about those so far? So you can give input to a program from a file, or you could write the output of a program to a file. That's kind of nice. What else? So if you give two dashes, two arrows, it will append to the file. So if it's already something there, otherwise it will overwrite. So this one will append, put it to the end. So like example and append to my file 1.txt. So let's go and look at that for a second. Here's file 1.txt. Right now it's got this as a file. If I run it and say append your output to that file, please, 42, 43. If I refresh this file, go back. There it is, 85. It's gotten added to that file now. That's kind of neat. Yeah, that's so give files to a program as input. You can get output and redirect it to a file or append. Are we good with those? Because the real power comes from this idea called a pipe. This character, this the thing above your enter key if you press shift. It's the pipe character, and you can now chain commands and give the output of one as the input to the other. That's where we're going with this. So this syntax, command 1 pipe, command 2 pipe, command 3 pipe, goes on down the line if you want to. It's going to run command 1 first, get the output, and then pipe the output as the input to command 2. Then it'll run command 2 with that, get its output, pipe the output as the input to command 3. It just like chains it all along. Does that kind of make sense? Like it runs this one first, boop, and it takes its output and gives it to command 2 as input. And it takes command 2's output and gives it as input to command 3. On and on down the line. It's wonderful. So there's some cool things that we could be doing there. So here are some options. Echo 4243 pipe / example. Does that make sense what I just did? Because what does echo 4243 do? It outputs 42 space 43. I gave that as input to example. It ran with it. It computed 85. Cool. Does that make sense? It's cool. I like it. So there's that one. Here's a weird one. I'll show this to you. It's a fun example. Let's do... What is a good one? Let's do... I'm going to need some options here. Hello world. Yeah, let me duplicate some things in this file. So here's, let's go back to file 1.txt. And let me add hello world at the end as well. So there's some lines that are duplicated, at least one of them, right? And here's something I can do with those. I can output the file, sorts all the lines. You need that for the next one. Unique without a E at the end. Creates, if it's in sorted order, it will go and extract only the unique lines. And then you can count with WC-L how many lines were in that output. Let me walk you through that. It's a little cool, a little weird, but cool at the same time. So let's see. So that's file 1. Let's put that on the bottom maybe. So there's file 1 on the bottom, and here are all the things I got. If I cat file 1, it looks like that. If I pipe that output to sort, it will sort the lines alphabetically. There they go. There are the outputs. And if I give that to a command called unique, it omits repeated lines. You can also tell it to only give you back the repeated lines if you want to call it with a certain option. So I can take that, sort it, give me unique, watch the difference. There's only one hello world now. And then you can ask for, there's a WC command that counts words or lines or something. If you give it the -L option, it will give you back how many lines there were. And so if we pipe all this to WC-L, it will give us how many unique lines there were in that file. Does that make sense? So that is us using the full power of the Linux terminal, of the Unix ideology. It's very cute, very cool. So yeah, I think that's most of what I want to say. Any questions about this slide? It's probably the most complicated one, but like the second you have and you understand all the different commands that exist in Linux land, like I highly encourage you to look into this. Like where sort lives, most of the programs live in /user/bin. If you do an ls of that, ls/user/bin, if you just do a man page lookup on most of these, so anyone that looks interesting to you, you might learn something cool. I don't know, or just do it and what's it called? There's so many. Or if you do just like go run, go do a tutorial for Linux command line stuff, and it'll teach you some of these that are useful. So yeah, if we're good with that, I just have one more slide to talk about some things with. I want to show you a few more commands, and that'll be it. So things that you may have not seen before. I like to use some of these. If you've used the, what's it called? You know, the autograder output, like look at your last submission score, whatever it's called, in the terminal. It uses a command called less secretly. What less does is it shows you a file that you can scroll through. It's like a lightweight version of Vim, but it's read-only. You can look at something quickly that way. So less, you can give it the name of a file, like less example.cpp. It's not going to highlight or anything. You can move around with the arrow keys if there are a bunch of lines, and then it's Q to get out of that, Q to quit. So that's what less does. It shows you a scrollable version of the file. So let's go to a file that we can scroll through, like lecture 20 or lecture 23's sure, merge.cpp. Like here I am scrolling through. I can use the Vim keys, I can use the arrow keys, and Q to quit. So if you just want to look at something very quickly, less will do that for you. Grep is a very, very useful one. What grep does is it searches for things. It searches for a string in a certain file. So you give the string you want to search for, then the file. So let's search for, I don't know, hello in our file, file1.txt, because we know it has a few hellos. Let's say grep hello in file1. And it'll tell you, oh yeah, here are all the lines where it matches and even color codes and highlights things. It's very nice. Grep-n shows you line numbers. It's very, very, very useful. If you're looking for something, like it'll tell you where it was in your file very quickly in just one command line call. That's that one. Diff is something that we use in the autograder quite a bit. It shows you the difference between two files, and you've gotten used to the syntax just naturally, the output, but I can try and show it to you now. So let's do, here's file 1. Let's make a new file called file 2. And what I'll do, oh sorry, let's do file1 underscore modified. Modify.txt. There, and I'll copy and paste all these things, and I'll change it up a bit. What do I want to do differently? Let's say, I don't know, hello world 42, and I'll add another line. There, I've changed them. So you can ask the diff command to tell you what is the difference between these two files in a nice, readable, compact way. You say diff, give the two names, file1.txt and then space file2.txt. And here's its output. It says, all right, that's how you read it. Starting at line 6 of the first file, you have some differences with the second file on line 6 and 7. So that's what it's saying. So here, I'm going to show you line 6 of the first file of the left file. I'm going to show you line 6 and 7 of the right file. And then it shows you some arrows to me like this. This was the stuff on the left file, the one that you gave first to diff. And then here's with the other one, like here's the stuff on the right file with a dividing line in between. So it's like, all right, on the left file, on line 6, it was hello worlds with nothing, and that was it. On the right file, there was a 42, and then there was another line. That was the difference between these two files. Everything else was the same. It did not show you those things. It's just trying to show you the differences. That's useful. So yeah, that's the thing. That's what that does. Yeah, that's most of it. Any questions about any of that so far? Because the rest of them, you've kind of maybe figured them out yourself by now, but remove removes a file, rm removes a file, then mv renames a file or moves it somewhere. Mv is short for move. So rm removes a file. Let me show that to you. So let's do some stuff. Let's put some stuff in places. I've got nothing but files all here. Let's make a folder. Make directory, I don't know, sample folder. So there it is. I got a sample folder. I can put stuff in that folder. So I can say move example output to the sample folder. So that's one way to move things. So if I look at ls, that thing's gone, but it's in the sample folder now. I can also give things new names and be like, move file 2 to file 3. That changes the name. That's moving the name rather than like the location. I guess technically you can think of it as the location. 3, file 2. And you can do the same thing as you move into folders. Like you can just give a bunch of slashes. Be like, all right, this renames. This, the second one is something I just did. Is like move a file into some other folders and keep the same name, still called foo.txt. And then the final, most powerful option is like take this file, put it in some other folder, and then also call it this. That's the last thing that you can do. Give a directory chain as well as give it a new name at the very end. So I can say that like move ls output into sample folder / ls output 2.txt. That's something you can do. So it's gone from this folder. It's in sample folder now, and it's called that. Does that make sense? So move renames or moves to places. Useful stuff. Let's put it back to how it was. So move ls output 2 back to ls output. There it goes. Back to normal. And we're back out here. All right, and then, yeah, remove gets rid of stuff. So let me make a copy of something. I don't know. Copy file 1.txt into file 3.txt. Let's see. So there it is. I can say remove to get rid of it. Remove file 3.txt. Now it's gone. There is no trash can in remove territory, so you have to be very, very careful. Did I spell that name of the file correctly? Did I do anything wrong? Because it is gone forever now. There's no recovering it. So maybe that's why you should use git to keep track of your changes. You can always get back to things if things go wrong. So there's that. If you want to delete a whole folder with things inside of it, you can say rm-r. The -r means recursive. Recursively delete everything ever, starting from there. That gets rid of everybody. So let me copy the sample folder. Copy sample folder. To copy a folder, you say cp-r for recursive copy. Copy that folder and everything inside of it, please. I'll just call it copied folder. So there it is. I got a copied folder now. It's got the same stuff inside of it as sample folder. If I don't want it, I can say rm-r copied folder. Now it's gone with all of its contents. Yay. So yeah, those are a few commands you maybe have already tried to learn, remove and move. Like you've probably run into those. I'm like, how can I do this on the terminal? But here's me spelling it out for you. And of course, the manual page will tell you more. There might be secret options. So I think that's where I want to stop for the day. Are there any questions about any of this stuff? Linux is magical. Question? That is not possible. Luckily, they don't let you do that. Yeah. And there is another command, just like there was mkdir, there's also a removedir, rmdir. If you do that on something that has stuff inside of it, like sample folder, it has stuff inside of it. If I try to removedir that, maybe that's the one we should be using. It's going to be, nope, I'm not going to do it because it's not empty. rmdir only removes empty folders. So that maybe is a better sanity check for you. But rm-r is just like, all right, I'm going to just set fire to everything right now. It's going. Everything and everything with it. So yeah, it's not possible. Because you can think of directories and files as a tree. And if you were to remove, like removing the parent without doing any of our special cases that we talked about, that's just not possible to remove that file, that folder, and have the files remain in some state of limbo. That won't work in the way that the Linux file systems work. So yeah, that's a good question. Other questions? It just won't let you do that. All right. One day you might implement a file system in an operating systems class. You'll learn how to make it look like a tree, and at that level, at the file system level, you can get rid of the directory and not the files, and they will be in limbo, but that's beyond the scope of this class. You should not be directly interacting with that unless you're the author of the file system itself. You don't let the user see that stuff. But yeah, you can have that power, but not through the Linux terminal commands. Yeah. So I think that's all that I wanted to say. If we are good, that's where we'll stop for now. There's a lot of stuff going on. We're almost done with the terminal commands. We'll get some more of those next time. And yeah, the last thing that I want to do is give you another lab. This will be a 3-week lab. Why not? I have a lot of time to do it. This might mean start early, right? You got 3 weeks. You shouldn't do it at the last minute. This one's your heap lab. All right, let's get to wherever I want to be here. Let's do starter code 41, lab 9. All right, so here is what we're doing. We're making our own priority queues with a heap on the back end. All right, so get all your files. You will be implementing, honestly, it's all in the files. You're going to be implementing a min heap. All right, in priority queue.h, you're going to be implementing a min heap, and you're going to be turning in only that header file, so that means it's templated. All right, that means you're using templates. So you should be able to put anything you want inside of your priority queue as long as you can figure out what's smaller than what, as long as there's a comparison operation. Yeah, there we go. So yeah, let's look at priority queue.h because that's where you're doing things. All right. It's a templated thing, so you got to do your work in the header file. So it's called priority queue. What the user gets to do is push something, push a T, pop. In our implementation is going to give back a copy of the thing that just got popped. Peak is going to give you the highest priority thing, right? Is empty, we'll see if it's empty, and length will give you the size of the number of things in the heap, all right? And then you got some private helper methods that I encourage you to implement and use. You don't have to, but it's probably in your best interest to do so. And then you got one member variable. Your priority queue is going to be represented with a heap, which we know should be a vector. It's going to be a vector of t's. That's your array that is really a tree secretly, however you want to think about it. Yeah. So yeah, that's what you're doing. And everything happens in this array. Okay. So you're going to be moving around your heap. And so you're going to be wanting to like go left and go right on indices now. So like, here are some helper methods that I think would be helpful for you to implement. Just like, all right, how do I get to the left child from an index that I'm at? It should be times 2 plus 1, right? Times 2 plus 1. Get to the right index from another index, give back, which would be times 2 plus 2. Your parent involves dividing by 2 in some way, and also maybe subtracting 1, if I remember correctly. So like use that to just like get around your tree, because then you're gonna, like, that's you going left, that's you going right. Getting indices back and going to those indices. So implement those helper methods for yourself to call, and then the rest is actual stuff. So I guess we should think about, yeah, just you're going to do all these things pushing. What should push do to put on the heap? Like you add it to the bottommost rightmost thing, so it's a pushback on the vector, and then you need to bubble it up, right? So you're going to implement that. It's in your book. Remember that. But that's push. Pop is going to remove, and also remember to give a copy of the thing that just got popped, the minimum thing. This is a min heap. We're using the minimum operation, like do a less than. And then, yeah, so that one's popped. So here's some helper stuff for that, some helper comments, like replace the root with the bottommost rightmost node. So you're going to be swapping with the very last index, right? Because that's going to be your bottommost rightmost thing. So replace your root, which is index 0, with the last index. Swap the guys. Remember to make a copy so you can return that. You're returning a T. And then you can pop back, right? That removes the bottommost rightmost node. And then that new root is way too small, no, way too big. And so you better bubble it down to where it needs to be. Okay. So that's going to be your popping. You remember the algorithm if you think about it, I'm sure. And then the rest of these should be very simple. Like peak, give back a reference to your current minimum. You know where that's going to be in a min heap very quickly, right? Is empty, give back whether the heap is empty. Get length, give back how big the heap is. You can use get length to implement is empty. It's going to be a very quick implementation for these guys. All right. Any questions about the priority queue classes methods. They're all going to be interacting with this heap array. That's what your heap is called. It's called a heap array. Yeah. All right. The only other thing that's not part of the class is make a heap sort function. You know that's going to be n log n. Mine as well. It's a optimal sorting algorithm for comparison sorting land stuff. That's a function. This is not part of the class, but it's templated still. All right. It's not a method, but you should make a priority queue of t's to do your heap sorting. Somebody gave you a vector of t's. You want to give them back another vector of t's that is that one sorted now. All right, so you're not doing it in place because it's a constant reference. You're giving back a brand new vector that's the original one in sorted order. So like here's an empty one to start. Fill it with the sorted things by placing all of these values into a priority queue of t's. Yeah, start popping them off in order because it's going to be a min heap. Min heap gives you sorted order, yes, ascending. Add them into the result vector and then give that back. Yeah. So that is heap sort, and that should do it. That's everything. I've made you some tests. They're doing some fun things. So here is a test on, like, I make a priority queue of ints, just making sure that everything is in the right order when you add them, like the top has been the correct thing when we peak. And if you start popping, you get back the right things in the right order, just adding 1 to 10. So that's a simple one, get that one passing. And then just for fun, because it's templated, I made a type called movie data, where I stole some movie data from the IMDb database. And so here's what a movie data object is. You don't have to actually look at the implementation of movie data.cpp because you're just using it. You're just using that type. It's somebody has made, oops, all of these operators. So a movie data can be compared in any way we could possibly want to compare it. And yeah, you just keep on. A movie data holds a name, a year, and a rating, and I've given it an order. That's what I've done. I've given it a way to be printed out as well. So where is that? So apparently the order it's going to be an order of a rating. That's what's going to happen. It's an order of rating, and it's got a way to be printed out so you can see what's wrong if something goes wrong. But here I am adding everything with their ratings. This is like the top ones. And then I put Frozen as 11 out of 10 because it's the best movie ever. All right. So that one should be at the very last thing when you heap sort, okay? Because it should be, oh, sorry, excuse me. Oh, wait, that should be the first thing because I remembered it backwards. This is going to order by greater than when you say less than. This is me making a max heap even though you made a min heap. Does that make sense for movie data objects? So do not be afraid when you pop Frozen off first. It had the highest rating. That's because I've changed the less than operation to mean greater than. See that? So you can do that. That's what it means to, like that's what we did on priority queues in the C++ type. It looked weird like that. So do not be alarmed. You're really making a min heap, all right? But you can change what it means to be min. That's that one. So yeah, that's it's just doing some tests and making sure that you can push and pop and it's getting the movies in the right order. Yeah. So I think that's all that I wanted to say. So you don't have to write any tests, just like get mine to pass. Like the int one in theory, once you get that to pass, the movie one should just come for free. But yeah, you're implementing the priority queue class and the heap sort function. You're using this underlying heap array that is just a vector of the kinds of things you're putting into your priority queue. Secretly heap. Yeah, I think that's all that I want to say. So the one thing you're turning in is a header file where you've put all your code. Any questions about this lab, lab 9? So this is the second to last one. We're almost to the end. Yay. So I think that's all that I wanted to say. So if we're good, that's all that I wanted to talk about, and I will stop the recording.